Devission and Germer experiment. This was in support of De-Broglie's theory. De-Broglie said that the electrons, when they move, then they are enclosed by a matter wave and its motion follow rules of wave motion. And when something which is moving in the form of waves like light, then it should be able to make the fringes due to interference, the fringes due to diffraction. That means in the light what we see, if a light cross an opening, then on the screen we get a central maxima. In the central maxima, the brightness is at the center maximum, then it goes on decreasing and to dark point come, where intensity is very less. Again it increases, again it decreases. That means that is a superposition and that is a interference, and that is possible only in the waves. If the moving electron follow this pattern, then we can assume that electrons move in a wave. Otherwise, if they don't do this behavior and they go straight, make the same size of opening as the size of image, then we will say they move in a straight line. To see this fact, to examine this fact, Devission and Germer made this experiment. In this experiment, an electron beam is created. For this creation, we use electron gun. Electron gun is 2 electrode. This electrode, this is a heater. When it is heated, then it emits electron. We know these are thermoelectrons. Okay, so thermoelectrons are heated here, which are negatively charged, and the positive of this battery is connected to this one shield, or we can say a passage. So electrons are attracted towards it. This positive voltage we can adjust by this rheostat, and we can see the reading from this. What is the potential difference between the two? And with this potential difference, we can always measure the energy, because we know energy on an electron is E into V. V is what? Potential which is drawing it. So just to measure it, to calculate it, we are having this voltmeter. This will give us what is the potential under which the electrons have been pulled with what much energy. Okay. Now these electrons, because of this energy, they are pulled here. That energy is converted into kinetic energy because they have velocity, and they keep on traveling like this, and this beam strikes a metal here. Now at one point we keep a metal. This is a nickel crystal. Nickel crystal is heavy molecules, heavy atoms, and for electrons it is difficult to displace them with their strike. So we have taken a heavy metal, nickel, plus we are able to see the structure of the nickel, and the nickel structure show that is set in arrays. Atoms are set in lines, and we have measured the distance between these two, and this is distance. Okay, and this distance is measured, and it is something like in angstroms. So this is 0.91 angstrom. This is known to us. Okay, this line of the nickel crystals, this can be rotated. We don't know, we can't see it, what is the line of atoms, whether it is like this. So we place it, just thinking it will be somewhere, we will come to know about it. Okay, then suppose that is the line. Now this electron beam strikes nickel and get reflected. When this gets reflected according to the slope of the atoms of the nickel, If it comes here, reflected here. If it goes like this, it comes here, it is reflected here. So we rotate it. We rotate it, and when we rotate, we find that when it is in this line, the reflection is here. We measure this angle. Then we keep on rotating like this. Here, reflection is here, reflection is here, reflection is here. Like that, we can make it at any place. Okay, but what we do is we keep the nickel at one place. Keep the nickel at one place and see how many electrons are reflected at this point, this point, this point, this point, this point and this point. That is another way of doing, and we do it that way. So this we make it stable, stationary at one point, and we are moving this collector. This is collector. When the electrons strike it, it gives us electric current in it, and that electric current is proportionate to the number of electrons which are falling on it. So we can always count the number of electrons which are falling on the collector, and we can always have a comparative idea whether the electron are less or more. Now this metal is here, electrons are striking it, and we are moving this. We are not moving this, we are moving collector. Now we make a table. On the table we write this angle of, this we will call angle of deflection. Deflection. And here we will write the number of electrons, or we will write the current, because current is made with number of electrons. And we make a table 1, 2, 3, 4. This deflection we start checking from here. And what is the angle here? 0. Then 10 degree, 0, 10 degree, 20 degree, 30 degree, 50 degree, 70 degree, and finally 90 degree. This. And we take the current at all the angles. This table is ready. After that, this is I1, I2, I3. After that, we make a graph. This graph is a radial graph and not a that Cartesian coordinate system, XY system graph is not there. This is a radial graph. In radial graph, what we do? This angle, for every angle, 10 degree, 20 degree, 30 degree, 40 degree, 50 degree, we draw one radius. So this is our radius, which is having all the degrees here. Then for 10 degree, we have the current I2. For 10 degree, here 10 degree, the current is I2. So we make a mark on it at this current. Then at 20 degree, current is I3. We measure from here. I increase, increase, increase. This is the reading of I3. So we make a mark here. Then again we see at 30 degree, at 50 degree, at 70, at 90, and we keep on marking them like this. This shows the current and this shows the angle. That is why this angle is given by this, and this length is giving the current. Now we have got all these points, and we join these points, and here we get a graph. At what angle electrons are maximum, at what angle electrons are minimum. So most of the times what we find that this is almost a straight line. But again we change speed of the electron How do we change the speed of the electron? By changing this potential. This will change energy of the electrons. That energy is converted into kinetic energy and speed changes. So with different speed, we make different graph. That means with different voltage. Say this is voltage 30 degree. Then we make a graph for voltage 40 degree, and that graph comes like this. Then we made a graph for voltage say 50 volt, or we made it higher 70 volt. For 70 volt we again see it is like this. Then we made graph for different voltage. Then for a particular voltage which was 54 volt, we got a beautiful graph, and that graph was, say this is 50 degree. That graph was like this. At this angle, 50 degree of angle of deflection. For 50 degree angle of deflection, we find the electron density is maximum. If we increase this angle, the density become minimum. If we decrease this angle, the density become minimum, and if we increase it a little more, again we find density has slightly increased. Here again density has slightly increased. You remember, this appears like a diffraction central maxima graph. This graph appears for electron when the setting is 54 volt and the maxima is made at the angle 50 degree. And this is the graph we were searching for. Now, once this graph has come, it has confirmed one thing, that all the electrons are not going to one point and all the electrons are not distributed uniformly. How they are distributed? They are distributed maximum at the center, then they go on decreasing. At this angle they are less, at this angle they are less. So when it comes here at 50, that is maximum, at 40 this is minimum, at 60 it is again minimum. If we go beyond 60, again it become a little more. If we go beyond this, it become a little more, and this graph gave us this. So this is a diffraction pattern. Had it been a uniform one, then we would have got a graph equal. We would have got a graph which is like this. But it is not this way. It is this way, and this is graph for the diffraction. Maximum, maxima, central maxima, decrease, minima, again increase. That is what has happened with beam of electrons. So, it is confirmed that beam of electron behaves like waves, and that is why it is able to make central maxima, which is possible by diffraction and by waves only. Now, can we find out the wavelength of this wave using this experiment? Answer is yes, they tried it. The formula for wavelength, we have seen the experiment of diffraction, and in that we know the elevation of first dark, elevation of first dark from the central line, elevation of first dark from the central line, this angle, that was A sin theta, path difference is equal to lambda. This was the condition for first arc. A sin theta. What is A? This is opening. Here the opening is this, the path difference. See, one beam, one part of the beam, some of the electron strike this surface and return back. Few more electrons pass these two atoms and reach this layer, second layer, and they are reflected by this. So there is a difference in the path. These are atoms located in the nickel. Okay. There is a beam of electron like this. The one strikes this, collide with this, return. The other collide with this, return. Both reach our collector. Now, which has travelled the longer path? Answer: this has travelled the longer path. How much longer path it has travelled? This one portion and this two portion, equal to these two distances. If this distance is d, then this is longer by d and d, 2d. So, what is the path difference between the two? 2d. If it is this way. But if this line is not like this and it is tilted by theta angle, it is tilted by theta angle, this, then this difference between the two, this path difference between the two will be 2d sin theta. 2d sin theta. So, path difference between the two waves is 2d sin theta, and the first arc is the point where path difference is equal to lambda. This we have done in diffraction. Once again, what is d? D is the distance between two layers. What is theta? That is tilting of the crystal. So that effective distance in this direction is not d, it has become less, and this is d sin theta. Now, the path difference is 2d sin theta is the path difference. If this path difference is equal to lambda, then what we get? The dark point. This is our formula for diffraction. Okay. Now, what is d? The distance between the two layers, and that is equal to 2 into 0.91 into 10 to the power minus 10 meter. Theta. What is this angle theta? What we have found, what was this angle? This angle was 50 degree for the best results. If this total was 50, then this is how much? 25. This is 25. Now, this is a normal to the surface. If this is normal to the surface, then this angle is 90 degree. If this is 90 degree and this is 25 degree, then this is what? 65 degree. So, this theta, which we call angle of glance, glancing angle, the angle from the surface to the glance, that angle theta is here. In this particular example, this theta was equal to 65 degree. How we calculated? Theta is equal to 90 minus 5 by 2. And this becomes 90 minus 50 upon 2. This is 65 degree. So, with this glancing angle fitting here, this is sine 65. This is equal to lambda, and we solved it. When we solved it, it comes to be 1.65. angstrom. So, by experiment in the laboratory, there are two things. One, we found that electrons are not distributed in a straight line, nor they are distributed evenly. They get themselves distributed according to diffraction pattern, making a central maxima and two dark points, and then again two bright points. That is a diffraction pattern. So, that confirms that electron travel in the form of waves. Then we found out the formula for wavelength, and that wavelength is equal to the path difference. We calculated by geometry, knowing the distance between two layers of the nickel crystals and the angle of glance. We could get the path difference equal to 2d sin theta. Putting the values of the distance between two layers of the nickel, which is 0.91 angstrom, and theta, the angle of glance, we calculated by this formula, which comes to 65. Placing these values, we got the wavelength of the electron wave, that is matter wave, to be 1.65 angstrom. That was experiment. But come to De-Broglie. De-Broglie gave us a formula that the matter wave linked with electron should have the wavelength equal to 1.66 upon root V. Now, what is the voltage here which has given us this result? Answer, this is 54 volt, and we put it here. Yeah, we can see that De-Broglie's formula was 1.227 upon root V angstrom. Now, we put here 54 root 54. Okay, whatever is the value of root 54, that we do it here, 7 point something, and then we divide it with this, and what we get is 1.66 angstrom. This is the result we get by the formula of De-Broglie. And this result very much match with the practical result received from this experiment of Devission and Germer. So, Devission and Germer did a diffraction pattern experiment, and they found that the wavelength of electron which is moving in the form of wave, the wavelength should be 1.65 angstrom. This is experiment. De-Broglie, only on the basis of his hypothesis, he found that the wavelength of electron at 54 volt should be 1.66 angstrom, and therefore we compared the two results. They are almost same. That means De-Broglie's hypothesis was correct. That means electron or matter travel in the form of wave. That hypothesis was correct. That means the material has got dual nature. It can go straight, matter nature, and it can go in waves when it strikes something. That is also correct. So, in this way, it was proved that material has got dual nature. Electron moves straight as a matter, it has got momentum, it has got a mass, but when it spreads, it shows wave nature. When strike, material nature, when spreads, wave nature. Similarly, light, when it spreads, wave nature, and when it strikes, then it is a photon, that is a material nature. So, light has got both the natures, material has got both the nature, material as well as wave. What is name of the material? Electron. What is the name of its wave? Matter wave. What is name of the material in light? Photon. What is the name of the wave? Electromagnetic wave. So, they have got electromagnetic wave in the wave nature, photon in the material nature when the light strikes a surface. Here, it is a matter wave when there is a travel of electron, and when it strikes, it behaves like an electron, matter. So, both are one and the same, both have got both the natures, dual nature. This is dual nature of light and matter, both. Dual nature of radiation and matter, both. Okay, De Broglie put the wavelength formula, that is 1.227 upon root V. There is maybe some confusion in the unit of this. The unit of this is nanometer. So, if we want to convert it to angstrom, this will be 12.27 angstrom. So, the formula, which is nanometer, when we convert it into angstrom, this will be 12.27 angstrom. Nano is 10 to the power minus 9, angstrom is 10 to the power minus 10. Now, if we put it in angstrom and we put the voltage, what is applied in this experiment, that was 54 volt, and this will be 12.27 upon root 54, and the unit will be angstrom, and when we convert it into the value, it will be, after calculation, 1.66 angstrom. So, please don't get confused, this is not angstrom, this is nanometer. So, remember, the De Broglie's wavelength for electron is 1.227 nano or 12.27 angstrom. Then you get the right result. Thank you.